Okay, so here we are in 6.2. We've got another example. This is page 17. And we're going to take a look at another example of a Laplace transform that involves a Heaviside function. But notice this isn't just a Heaviside function by itself. So we have a function times a Heaviside function. And on first glance, you might think, is that a shifted switch? Doesn't look like it. This thing is just t squared, and this is turning on at u equals or t equals 1. So this is not in a standard shifted switch. This is not a, I should say, in the form of a shifted switch. So we're going to have to do some work here to make this happen. So just a reminder, if we wanted to, we could convert this into a piecewise function, and this thing is going to behave like 0. And by the way, we're taking the Laplace transform of this thing. We're going to take the Laplace transform of something that behaves like 0 as long as t is less than 1, and then it behaves like t squared thereafter whenever t is greater than or equal to 1. So we're going to figure out what's going on with this. Now, we could, if we wanted to, use the integration definition, right? We could figure out this thing use the integral definition of the Laplace. But the problem with that is it's tedious, and there's other ways that we can do it. So without having to do any calculus, we can also really get this thing to work. The problem is what we really want. We want something that's the shifted switch version, so we want something that looks like this. T minus 1 quantity squared times u sub 1 of t. This would be perfect. This would be the perfect shifted switch. That's a shifted switch form. And that would be wonderful. If it started off that way, we'd be done already. So what I really need to be able to do is to manipulate this a little bit. Find a way to manipulate this a little bit. So we're going to play some little algebraic games and say, well, what the heck is this t minus 1 squared business going on? What is t minus 1 squared equal to? Well, if you multiply it out, that's just t squared minus 2t plus 1. And that right there, that t squared, that's actually what we've got in our original problem. So that is, if we move everything else, kind of shift things around by itself, this is what we could substitute for. So all I need to do is rewrite this thing. I'm going to rewrite t squared in terms of this part, and this part. So I'm going to move these two terms to the other side. And I'm going to say t minus 1 quantity squared plus 2t minus 1 is the same thing. This thing right here is the same thing as t squared. And so, yay, we've got something that's shifted right here by 1 unit. And so that's good. That's happy. That's yay. The only problem is the thing that's right next to it is not shifted. This is not shifted by 1. And so that stinks. So I'd love to be able to just throw this chunk, the right-hand side, in and replace the t squared with that, but I can't really do that. But I can play a little game with algebra since we've been doing this all along. I'm going to keep going and say that t squared is just equal to my shifted t minus 1 quantity squared plus 2 times, and now inside here, instead of t, I'm going to make it t minus 1. But I can't just create minus 1 out of thin air, so I'm also going to make it plus 1 on the inside. And if you're thinking, well, wait a minute, you didn't do anything, you're absolutely right. I didn't change anything. It's still 2t. But now, if I multiply this 2 times the 1, I'll have t minus 1 quantity squared plus 2 times t minus 1 plus 2 minus 1. Or t squared is equivalent to t minus 1 quantity squared plus 2 times t minus 1 plus 1. Now, what I've just done is I've rewritten my original function that was not shifted in terms of two chunks that are shifted by exactly the amount that I want. And that means I can replace this t squared, way back in my original problem, I can replace t squared with all of this as one kind of factor. So that means going back to my original, I can now say, what's the Laplace transform of t squared times u sub 1 of t? Why, that's the same thing as the Laplace transform of t minus 1 squared times u1 of t plus 2 times t minus 1 times u1 of t plus u1 of t. Now it looks like I've made a whole lot more work for myself, and in some ways I have, but I've now rewritten my original function, which was not a shifted switch, into a series of shifted switch, say that 3 times fast, and then the last one right here is just a Heaviside function that I can figure out what's going on. So this really is the same thing as the Laplace transform of this first one, which is a shifted switch, plus 2 times this one, which is also a shifted switch, plus the last one, which is, 2 times the Laplace transform of the Heaviside function, which switches at t equals 1. So for each one of these, I have a shifted switch situation. So I'm going to use that formula from the previous page and say e to the negative as, a is the amount that we're shifting, times the Laplace transform of the unshifted function. And so for this first one, it's going to be e to the negative 1s times the Laplace transform of the unshifted function, which is t squared, plus 2 times e to the negative as, or negative s in this case, because a is just 1, times the Laplace transform of the unshifted function, which is just t, plus the Laplace transform of the Heaviside, switching at 1. So in this case right here, e to the negative s, the Laplace transform of this, we know we have a formula. You remember that's going to be the power for your polynomial, the power factorial divided by s to the power plus 1. So this one's going to be e to the negative s times 2 factorial over s to the 3 plus 2e to the negative s times the Laplace transform of t to the first power, which is just 1 factorial over s to the 1 plus 1, or s squared, plus the Laplace transform of this guy right here, which we know is just e to the negative s over s. And so we can simplify this down a little bit and get e to the s times 2 factorial is 2s over s cubed. So this is 2e to the s over, e to the negative s over s cubed plus 2 times 1 factorial is 1. So this is going to be 2e to the negative s over s squared plus e to the negative s over s. Now, if you notice the pattern here, we have s cubed, s squared, and s to the first power in the denominator. And that's not a coincidence, since we were taking the Laplace transform of a t squared. Notice we wound up with denominator s cubed, denominator s squared, and a denominator s to the first terms. And if you kind of think back to our classwork problem where we sort of expanded this guy out, whenever you're taking the Laplace transform of a polynomial of degree n, you always wind up with a degree n plus 1 in the denominator, so s to the n plus 1. So there's a good reason for that. So of course we can check this by jumping into Maple as well and typing it in. We can type in the Laplace transform. I'll do that off screen here. So poof, like that. I have the Laplace transform of t squared times the Heaviside function t minus 1, so that's the unit step function at 1. And sure enough, when I hit enter, I get the exact same result, just in a slightly different form as what I had before. So if I divide each one of these terms by s cubed, I get exactly what I had before. 2e to the minus s times over s cubed, 2e to the minus s over s squared, and then e to the minus s over s. So it worked. Yay! So this little trick of being able to rewrite a function in terms of a shifted switch, you have to have an idea of what it is that you want the shifted switch to look like, and then you play some little algebra games to make it thus, right? There's a couple of different ways you go about it, but this one seems to make sense to me. We want it to be t minus 1 quantity squared, so we rewrite t minus 1 quantity squared in terms of other shifted switches. So the last little chunk that we're going to do for this is the Laplace transform of our standard step function. Looks like this, which means that the inverse Laplace undoes that. So no big shakes here. This is just us saying that if you can take the Laplace of a step function, you can take the inverse of something and get a step function. So rewriting our shifted switch functions, being able to write the Laplace of a shifted switch or the inverse Laplace that yields a shifted switch, that just becomes handy. So at the very bottom of this page, there's an example that we'll kind of play a little game with here, algebraically. I want to take the inverse Laplace of e to the minus 2s over s squared. And so that should look pretty familiar, because if you're kind of paying attention, then we should see evidence of shifted switch going on. So let me rewrite this in a way that may make a little bit more sense. So I'm taking the inverse Laplace of e to the minus 2s times 1 over s squared. Now, if you notice, we've got a value in the upstairs of 2, right? So that's giving me a sense of how much to shift. It's shifting 2 units. And this thing right here gives us the Laplace transform of a known commodity, right? This right here is the Laplace transform of a polynomial. As a matter of fact, it's of a function being shifted. So the question is, what's the function that we're shifting? What's the function that has this as a Laplace transform? And of course we can head back to our table and say, okay, 1 over s squared, well, that would be like if n is 1, it would be 1 over s squared. So it really is t to the first power. So what we're going to wind up seeing is this really is the Laplace transform, the inverse Laplace transform, turns out to be u with a little subscript 2 of t, and we get that from this chunk right here. I'm not going to use green, I'll use a different color so it stands out a little bit more. This piece of it right here turns into the shifting function, or the stepwise function of sub 2, and then the second part will be times not just t, but it's going to be t shifted 2 units. And you can get that from this guy right here. And of course, it's the function f of t shifted 2 units. So it takes a little while to kind of get used to this. And fortunately for us, we've got Maple to do a lot of the heavy lifting. But I wanted you to see how we can go from inverse, or we can go from a Laplace transform back to a function of t and produce something that actually has a heaviside function. So there's one more example at the end of this section, and I'm going to make it into a separate video just to kind of space some things out.